So, you want more Desmos, huh? Maybe you've watched Learn SAT Math's Desmos video, or Tutorlini's series, or Reshop Jane's Desmos tricks. Well, I'm here to tell you that there is so much more. Maybe you already know me, maybe this is your first time seeing me, but it is finally come, Adyar's Desmos Guide. So, what are we going to do today? Well, I'm going to give you the foundation of everything that you need to know in order to learn Desmos fully. This is not basic Desmos guide, as some of you may know. Enough of introduction, let's get into it. Desmos, what is it? Well, it's a calculator. So what that means is it does basic arithmetic, it does your plus, it does your minus, it does your divide, and it does your multiply. It also is a graphing calculator, so it makes graphs, it makes lines, it makes really anything you want. And the third thing that it does is the part that most people skip out on. And it's the part that can speed up every single problem, called regression. And some YouTube videos cover this a little bit. What regression is it solves for variables. It solves problems for you. And I feel like this is such a cheat, and it's crazy that so many people don't know about this already. So here I am, and we are going to learn all about it. These are the three main functionals of Desmos. There are really only two things you need to learn how to use in order to start playing around with everything that you can with Desmos. So the first thing are the variables. There are two types of variables. I call infinite variables, which I'll label IV. And the only two types of variables that are infinite variables are X and Y. Those are your only infinite variables. And I call them infinite variables because what happens when we put in X? Well, it makes a graph. And this graph goes on, you guessed it, for infinity. So it really holds no strict value. And that's what X and Y does. As you can see, the same with Y. It draws a graph for infinity. So those are your only two infinite variables. Now, the second type of variable is what you call specific variable. Specific variable, they hold specific values. And they can be denoted with any lowercase letter, A through Z, excluding X and Y, and E, excluding X, Y, and Z. They can be any capital letter, A through Z, and they can be any letter, uppercase or lowercase, with a subscript. Subscripts turn anything into specific variables. So I can give you an example of what a specific variable might be. A equals 5, B equals 6. You can also do capital X equals 9. We can do X1 equals 7, and I'm just typing in X and the number 1. It auto subscripts. And we can even get really big subscripts by we can press Shift minus, and we can get as big of a subscript as we want. We can do numbers, letters, and sometimes I like using this to write answer. So we could do answer equals, 9. And what this does is it stores a number value to a specific variable. So now if we said, what is A? It gives us 5. What's 5A? Well, it's 25. What's 5 plus A? It's 10. So now these specific variables are treated exactly like regular numbers would. And that's all there is to specific variables. They hold specific values. And I say values plural because I will get into that later. So two types of variables. And then what's the second part of Desmos that I was talking about earlier? Well, the second part is going to be our equals. There's actually two types of equals. There's going to be our regular equals, and that, can make graphs, or like how we used it with the specific variables to store values. And we'll get into that a little bit later. But the second type of equals, it's called a tilde. And you can get it by pressing Shift and then the backdash above the tab key if you have a regular keyboard. And tilde is the second type of equals. And so if we now pair them up in a table and we put these two together, we can get a table that has our two types of equals and our two types of variables, infinite variables and specific variables. So what happens when we use infinite variables with the equal sign? Well, let's demonstrate. We get a graph. What happens when we use infinite variables with our tilde or our regression equals? We get an error. X may not be used as a regression parameter. So basically what that's saying is that nowhere in the same line, these are called lines, line 1, line 2, line 3, in this same line, you're not allowed to use a specific variable with a tilde. So if you're getting an error, make sure that you're not using an infinite variable with a tilde. Okay, a specific variable with an equals. What does that do? Well, we were using it a little earlier. If we have a specific variable and we use an equals, that stores a value to the specific variable. And this can get a little bit more complicated later. Like if we say, B equals 5 and A equals 1 plus B, that also works. The most important thing to know is that when we're using specific variables with the equals sign, we have to make sure that we have one specific variable on the left side of this equals, and then anything we want on the right side of the equals. So if I tried to say 5A equals 10, this would not work because we have to have just one specific variable on the left side of the equal sign. So we'd have to divide this 5 over if that's what we wanted to mean. So a equals 2. I call this a strict definition, and that's because we're strictly defining these. We can use this a now, since we defined it once strictly, however we want, in as many lines as we want. 5a, 5 divided by a, 7 plus a. We can use it forever and ever, and it will always work. It's a strict definition, and that is a's value. Our final pair is a regression with a specific variable, and that is the most fun part of Desmos. That solves variables. Or really, it solves our specific variable. I'll give you an example. We have a specific variable a, and let's say, we have the equation 5a plus 2 equals 12. Well, if we tried that with a regular equals, 5a plus 2 equals 12, it doesn't want to work. And that's because when we're using equals, we have to have just the specific variable on this left side, and that's not the case. What if I'm too lazy to solve this by hand? We replace this with a tilde, and it solves a for us. And this will work almost all the time. There's a few specific instances where it won't work, and you have to play around with it yourself to understand why. But if you're using it correctly, this will always work. You can put a wherever you want. The square root of a plus 4 is 20. Boom, it solves a. Now, an important thing to know is that it will only give you one value for a. So for instance, if we replace this with x, right? And now we have an infinite variable, and we replace this with equals. So now we're having an infinite variable with a equals, we're going to get a graph. Now we can zoom out and see our value is this line right here. And what if we change this to a square? Well, you would see now that there are 2 values for x. And if we now put this back to a regression, we only get one answer. And that's because regression will always give you the value that's closest to 0. And if they're equidistant from 0, then it'll give you the positive value. So if we had something maybe like x minus 3 squared, we can see that there's 2 values, -1 and 7. But if we now replace this with a regression, so changing the infinite variable to a specific variable and changing the equals to a tilde, we can see that it gives us -1 because -1 is the closest to 0. That is really the foundation of everything there is to know about Desmos on the SAT. And from here stems so many intricate ways of using Desmos that are really awesome for the SAT. However, I think I will save that for future videos because I really want to focus on the main implications of these 2 types of equals and these 2 types of variables. So I'll be playing around with it so that by the time our next video comes where I dive into some more advanced problems and usages of these functions, you have the basic foundation, you know how Desmos is thinking. That's really my goal, because once you know how Desmos thinks, then you can problem solve any problem that you see on the SAT and just give it to Desmos in the language that it understands. I'm going to go over the 4 types of graphs that you can do, and that's just all inside of here when you pair an infinite variable with an equals. So I'm going to split them up into visual graphs and mathematical graphs, or graphs that you can do stuff in the terminal with. So we have our visual graphs, which all they do for us is appear right here visually so we can look at them. We're going to have 3 of those. It's going to be our y equals x, and y minus x equals 0. And I'm going to explain why each of these is different. So while they all make the same looking picture, they behave a little bit differently. And that's why I've separated them into these 3 categories. So the first one is what you would see on a TI-84. It starts with y, and you get y equals 5x plus 3. Y equals x over 5 minus 2. Y equals x squared. It's something like you would see on a TI-84. And it's only visual. I mean, you can see these little highlighted parts. But other than that, it does nothing for us. You can just take out the y equals, because if you have something that looks like a y equals function on Desmos and take out the y equals, Desmos automatically puts in that y equals. So really, 1 and 2 do the same thing, except you're wasting time by adding this y equals. So moving on to our second type of graph, it's the exact same as y equals, except without the y equals part. You can just type in whatever you want, and Desmos will automatically put in a y equals in front of it, as long as you only have x's. Because although y and x are both infinite variables, Desmos treats x and y a little bit differently. So if we type in y, it's not going to make a graph. And why? Because Desmos is automatically inserting the y equals y into that. And when you have y equals y, that's infinite solutions, and therefore Desmos is blank. And then for the final, this has some usages, right? So if we get some weird, funky graph and it can only be represented in some visual way that we want to see and we don't need to use later on and reference, we can get a random assortment of y's and x's to make a graph. And that means just putting y's and x's wherever we want on either side of the equal sign. So while it only makes a visual, it has the most usage, because if we have some sort of weird graph like y squared minus the square root of x equals 1 over x plus y, we can get a visual representation of this, right? It's really weird, but maybe for some reason we need it, or maybe that's a little too funky and we can get this. It allows us to see the most visually advanced functions, but we can't really do anything with us as far as working with it in this terminal area. But it still does give us our mins and maxes and points that it thinks is important. And my favorite type of graph is the non-visual. There's only one non-visual graph, and that's going to be our f of x equals x. This is the greatest function there is. And why is that? Well, because although it might look like the same thing as y equals x, it's not. What we can do with this is we can put in numbers. So f of 1, it gives us 1. F of 2, it gives us 2. And if we were to change this function, x minus 2, we now get these values we can use in the terminal, and it remembers it forever. This is really awesome because I like to do my problems as quick as possible. And oftentimes that means not having to look at this graph, not having to write down my paper. So if I can come up with a function, I would like to reference this function whenever I need to. And the crazy thing is we can actually mix this with a regression too. So if we get something like f of 5 equals 3, which is true, what if we wanted to know what is the x value when the y value is 3? We can put in a specific variable and we can use regression, because regression plus a specific variable gives us a solved equation. So if we put in 5 here, now we get a equals 7. If we get what is the x value when y equals 3, we get a equals 5. So you can pair this visual plus terminal, really. It does both. And at this point, we have so many different usages of functions now. You know, we have solving for y when we have an x, solving for x when we have a y, and it really opens the door up to a lot of different possibilities when we have this f of x type function. Now I want to introduce you to two little concepts that we'll go over a lot in following problems and videos. And the two main ones are, and really it all boils down to an element list. So I guess it's just one concept, the element list. And this is such a goated function for so many different reasons. It allows us to do tons and tons of different things. What the element list is, it's a group of numbers. So if we call a equals 1, 2, 3, this specific variable, we're now giving it the specific values of both 1, 2, and 3. And this allows us to do a lot of different things, and it's split up into two main categories. So we have statistics, so we can have now the mean of a, we have maximum of a, the minimum of a. We can get the range by subtracting the two. We can get the median. So many different statistic things that we can do with this element list. And the second one, it's called a system of equations. And you might be wondering, well, how in the world do we get a system of equations with an element list? I'm going to show you. Say we have the system of equations x plus y equals 10 and x minus y equals 4. Now, this might seem easy to do, but I'm going to give you this easy problem to demonstrate the system of equation. If we graph this, we can get the different values that x and y can be, right? These are all the different possible values. And what YouTubers will show you is you can go x minus y equals 4. Oh, that's crazy. We have a system of equations and this is our solution, right? Well, there's a better way to do this actually, because as soon as we introduce a new variable, we cannot any longer do this, because if we try to introduce a new variable, it doesn't know what to do. Maybe with three-dimensional Desmos, but we don't have that. And what if you wanted 4 unknowns? Well, I'm going to show you a way to do this system of equations without looking at the graph. So, we might turn to regression, x plus y equals 10, or regression, tilde 10. And you can see it's not working, and that's because we're using infinite variables with a tilde, which never works. x1 plus y1. That's an easy way to turn infinite variables into specific variables, or I could just convert it to a and b. Either way works, but I like using x1 and y1. So it's giving us this value that's chosen. It's chosen 10 and 0 because it wants to get one of these variables to as close as 0 as possible. You might think, okay, well, let's plug in this second function now, and it should solve this system of equations for us, right? x1 minus y1 tilde. for regression. And you can see there's a problem. When we use regression on specific variables, it gives us an implicit definition. And up here, I said a strict definition because that's what a specific variable gets when you use equals. But when you use a specific variable with a tilde, it solves the specific variable, but it gives it an implicit definition. So what that means is that it won't remember the value. And you can see that here. It doesn't remember what x1 is when we're trying to do this. These lines don't work together. They work completely independently and they don't do anything together. So how do we get Desmos to take in these equations together and solve for when they both happen? Well, that's when our element list comes in handy. So what I'm going to do is I'm going to open up a bracket. I'm going to take this left-hand side here. I'll call it the left-hand side 1 because it's in line 1 and it's on the left-hand side of this tilde. And then we're going to separate it with a comma. Then we're going to put this left-hand side of line 2. And now we have just put in both of the left-hand side. And now I'm going to do our regression again, or our tilde, and we're going to set it equal to this right-hand side 1 and this right-hand side 2. So now what is it thinking? So what Desmos is doing is it's thinking both this equation, which is thinking that this equals this, x plus y equals 10, but it's also in the same line, including the equation x minus y is 4 right here. X minus y is 4. So the first term in this element list is set equal to 10, and the second item in the element list is set to 4, which is the second element in this other element list. So we can, at this point, add on all of the variables that we want. So what if we had something like before? Z plus x plus y equals 10, z minus x minus y equals 4, and z plus y equals 22. I don't know if this will even work, but we can try it. So what will I do? I'm going to add a third element in this list, and we're going to call it, we can stick with the format, even though z is a specific variable, z works. I'm still going to add a 1, but we do in fact need that 1 on the y. Okay, and then the third element in the second element list that we're regressing is going to be 22. And what do you know? It solves it for us. So it will give us values for x, y, and z that meet all these terms, all these equations. And that's something that you can't do with the method of system of equations shown in every single other Desmos YouTube video. So what is it doing? Well, it's saying first term equals first term, second term equals second term, and the third term equals the third term. And we can do that with as many equations, as many unknowns as we want. The important thing to know is that you have to have the same amount of unknowns as equations. So what's important to know is that the amount of unknowns that we have has to be less than or equal to the amount of equations that we have. And it works the best when the two are equal because it will give us only one value. But if we have more equations than unknowns, then we run the risk of it not working because we're over constraining it really. We're giving it too many equations to fit all of these. If we have more equations than unknowns, then you just have to know for sure that it's possible for a certain set of values for x, y, z, whatever your unknowns are, to fit all of these equations. But that's not really Desmos. That's just more math in general. Okay, so what else can we do with this element list? So I know I divided it up into really like a statistics and system of equations, but there are more things you can do with element lists. And the first one is graph regression. And most videos that I've seen skip over the fact that this is an element list. But when we add a table, we can type in table right here. When we add a table and we set it to 1, 2, 3, 4, 5, 6, and we get these points right here, what that's really saying in Desmos's head, it's the exact same thing as if we went, I'm going to use x2 for this one. X2 equals 1, 2, 3. Y2 equals 4, 5, 6. And then we just graph x2, comma y2, these points. In Desmos's head, when we type in this table, it does the exact same thing as setting an element list for these two and then just graphing the points. But a table does sometimes come in handy if we want to do this really quickly. But just know that it's really, a table is just an element list. So how do we do a regression with a graph? So that's when we're saying we have a certain standard equation. So whether that be y equals mx plus b, or y equals ax squared plus bx plus c, a quadratic, or maybe we have a exponential, y equals a b to the x plus c. whatever it may be, you can get Desmos to make you a graph that fits points that you have in this element list. So let's try that. So we want to type in y1, which is just this header right here. We're referencing this header up here. And then we're going to say, let's try a linear line. So we can go im x1 because we're referencing now these x values, and we'll go plus b. And it gives us a line that goes through these 3 points. So let's try a quadratic. ax1 squared plus bx1 plus c. It gives us, technically this is a quadratic, but it's saying a is 0. So how do we fix this? What if I actually want something that looks like a quadratic? And this is where domains come in. We could set a has to be greater than 0. Maybe 1. We can do that, and it will take the shape of a quadratic. But what's important to note is sometimes it's impossible to make, a quadratic that will fit all these 3 points. Now on the SAT, you won't have this problem. If you're ever going to use graph regression, the points, if you do it right, will always form whatever type of representation or whatever model, whether it be quadratic or linear, that it gives you. But you can see here that we have now made a graph that makes sure that a is greater or equal to 1. But we see down here that now r squared is 2/3. And that's because when we set it perfectly, r squared should be 1 if it perfectly aligns those points. But as you can see, if it's off, then r squared will be something that's not 1. And so this is a good way to check to see if your points are perfectly fitting your graph, or your graph is perfectly fitting your points. So what if we were to change this to something like 8? At this point, maybe there is actually a better quadratic representation of this. So ax squared plus bx1 plus c. And now you can see that r squared is 1, which means this graph perfectly fits these points. So this concept can be used for a lot of problems, which I'll, go into future videos. But I think the most important thing to note is that similar to our system of equations, the amount of specific variables that we're solving for, so in this case, A, B, and C, has to be either the same or less than the amount of points we have. So think of these points in your table as equations, and your unknowns are right here. So in a system of equations, you have to have, the same amount of equations as you do unknowns. In the same sense, you have to have the same amount of points as you do variables. And what happens if we don't? Well, we get tons of different graphs that this could be. So you can see here now that we only have 2 equations. When we add a slider for A, that'll give us so many different parabolas that fit these 2 points. Tons of them. You can see it right here. All these graph fits these 2 points. And that's because we don't have a third point to fully constrain this parabola. So as soon as we have a third point, we have a fully constrained parabola. And it will give us what the values of each of these are. So similar to the system of equations, our amount of points on the table has to be greater than or equal to the amount of unknowns we have. But why I say greater than or equal to is if we just so happen to, I could go down here and calculate what a third point might be. If we go f of x equals ax squared plus bx plus c, and I go now f of 5, we get 12. If I type in 5, 12 right here, you can see now we have more points than unknowns, and it still works. See? And there's only one parabola that fits these 4 points, and it's this one right here. So it does technically work in only making one parabola if we have more points than unknowns, but we just have to have the perfect point if we have more points than unknowns. If we change this number even slightly off, you can see that our r squared value becomes less than 1. And if we go even lower, we don't have a parabola that perfectly fits it. So if you are going to add more points than unknowns, make sure that r squared still stays 1 so that you know that all the points perfectly fit it. I think that is all I'm going to do for today. That introduces most of the main concepts that I use when solving questions with Desmos. And be prepared for my video explanation going in depth of each of these problems in the guide that you can find in the description. Thanks for watching, and later.